This is video 2 for the simple harmonic motion. So in the previous video I mentioned that as an AP student you were responsible for two types of oscillators, the mass spring system and the pendulum. So in the last video we talked about the mass spring system. In this one we're going to talk about the pendulum. So for a simple pendulum, the period will increase with the length of the pendulum and decrease with the magnitude of the gravitational field. So keep that in mind. We're going to have to, when we get our formula for period, those two things should be true. Let's begin by making a diagram of the forces acting on this pendulum. So looking at this, we see that we have a tension force coming up here, and we see that we have a gravitational force. Now this gravitational force, what I can do is I can make a Cartesian coordinate system, and I can resolve this gravitational force into its x and y components. And notice that the angle that I pull the string at is the same as the angle here. On that y-axis we will have equilibrium, so the tension force will equal that FGY. So honestly that's not nothing very exciting right there. But on the x-axis we see that we only have one force. So when we study the forces, the net forces on that x-axis, we get that FGX, which equals MA. And I'm going to say this is a negative force as well because it's kind of pointing to my negative x-axis. So then, looking at this, FG is obviously mg, and we see that we have to use the sine function to get that FGX. So we're left with negative mg sine of theta equals ma. And we can see then also that the mass of this bob will cancel. All right. So we need to figure out what that angle theta is. Well, notice that I could represent this string as a right triangle, where the hypotenuse would be the length of that string, and then this distance that I'm pulling it away from its equilibrium point, I can call that x. So then, SineCosine sine of theta equals opposite over hypotenuse. Now here's something that I'm going to introduce. This is something called the small angle approximation. What the small angle approximation says is that for angles that are less than 15 degrees, sine of theta equals theta. That is the small angle approximation. Now we want to convert the degrees into radians, so whatever the radian equivalent of 15 degrees is, sine of theta equals theta. So we know that sine of theta equals x over L. And we know that sine of theta equals theta. Therefore, theta equals x over L. So basically, what we can do is coming up here for the sine of theta, I can replace that with x over L. So what I'm left with then is negative g times x over L equals A, where L is the length of the string and x is how far we have pulled the string away from its equilibrium position. All right, now realize that acceleration is the second derivative with respect to position. So I'm left with negative g times x over L equals d squared x over dt squared. And rewriting this, I can rewrite this as negative g over L times x. And hopefully you notice that this then, again, is another second order differential equation. And I can rewrite this again as the equation for simple harmonic motion. So that means that the angular frequency, which is 2 pi times frequency, frequency is 1 divided by the period, so that means the angular frequency, omega, is 2 pi over period. So that's one equation. And then also looking at this, we see that omega would equal g over L underneath a square root. So when I put those two together, I see that the period, t, would equal 2 pi times L over g under square root. And that is what you need to know right there, that formula for period. And notice that as the length of the string gets longer, the period gets longer, and as the gravitational field strength becomes weaker, the period gets smaller as well, or bigger. So as g becomes bigger, t becomes smaller. As g becomes smaller, t becomes bigger. So that obeys that statement that we have up here. This model only works for angles less than 15 degrees because we use the small angle approximation to create this model. That's very, very important when you go to conduct experiments involving pendulums. When you pull the string back, you have to make sure that you stay under 15 degrees. And we'll do some work in Google Sheets and things like that, and I'll demonstrate the small angle approximation and how powerful of a tool it truly is. Now, what's kind of neat about simple harmonic motion is that we can represent it as a sine or cosine graph. So here, imagine that I have my mass spring oscillating up and down, and I attach a pin to it, and I roll some paper underneath of it. Notice how, as we roll this, it would produce that sine or cosine graph. Likewise with a pendulum. If I let it oscillate back and forth with a pencil attached to it, and if I roll some paper underneath of it, how I can get a nice sine or cosine graph. So some things that we can have here then is we can have our amplitude. So think of this amplitude up here as x, and this amplitude down here as our negative x, and then this position right here as our x naught. We can have wavelength. I represent wavelength with the Greek letter lambda. And the amount of time it takes to complete one wavelength would be the period. And then frequency, measured in hertz, would be 1 divided by the period. Now, when we look at a sine wave like this, we can represent it with the formula a times sine, and in parentheses, omega t plus kx. So this is like the general equation for a sine wave. And we can easily replace the sine with cosine, and it would be just as true. So let's take a look at what we have here for our general equation. And again, this can be used to model simple harmonic motion. So the y is your current position on the y-axis. Or you can think of it as the current amplitude. A is the maximum amplitude. Omega, again, is the angular frequency. Where omega equals 2 pi times the frequency. T is for time. You know, how long has this thing been oscillating for? K. K is something you probably have never seen before. This is called the spatial frequency. And K is going to equal 2 pi divided by the wavelength, lambda. So you can think of, if angular frequency is how many wavelengths happen per second, spatial frequency is like how many wavelengths happen per second, but in terms of meters instead of in terms of seconds. X is going to be your current position on the x-axis. So you can kind of think of like your current wavelength, if you want to think of it that way. So as an example, let's take a look at this formula right here. So we got y equals 0.6 sine 4t minus 10x. So again, this is modeling some simple harmonic motion. And we want to pull all the information we can from it. So first off, I can get the amplitude. So the maximum amplitude is 0.6 meters, or 60 centimeters. So this thing was originally displaced from equilibrium by 60 centimeters. And this could be a mass spring oscillator or a pendulum oscillator. It doesn't matter. It'll work for both. The next thing is I can find the frequency. You see, angular frequency equals 2 pi times frequency. So then frequency must equal omega divided by 2 pi. So for this case, the omega is 4 over 2 pi. So the frequency is 2 over pi hertz. The next thing we can find is the period. Period, let me start the other way here. Frequency equals 1 divided by the period. So period must equal 1 divided by the frequency. So I got 1 divided by 2 over pi hertz. So the period then is pi over 2 seconds. A hertz is a 1 per second. So obviously invert that again, you get seconds. So we can figure out how long this thing has been oscillating for. Or not how long, but how long it takes for one wavelength or one complete oscillation. The next thing we can find is the wavelength. So the spatial frequency, k, is equal to 2 pi divided by our wavelength. So then our wavelength must equal 2 pi divided by our spatial frequency. So that means we've got 2 pi divided by 10, which equals pi over 5 meters. So that's our wavelength, pi over 5. And finally, I can find the velocity. Velocity, which is displacement over time. Well, for a wave, they maintain constant velocity. So for a wave, the displacement is going to be the wavelength, and the time is going to be the period. So I've got pi over 5 meters divided by pi over 2 seconds. So that equals 2/5 meters per second. So just from this one equation, I can get 5 pieces of information, which is kind of impressive. All right. Be a little bit of a longer video, but we don't have very much left to go, so let's go ahead and finish up these notes. Energy. So a system with internal structure can have internal energy. Changes in the system's internal structure can result in changes in internal energy. What that statement means is that we can apply conservation of energy to help us understand how the system changes as objects oscillate back and forth. So as something oscillates, it's going from potential energy to kinetic, back to potential, back to kinetic, back to potential. It's going back and forth between those. So for conservation of energy, when there are no conservative forces acting on a system, the energy in the system remains constant. So when we take a look at some graphs here, what this graph represents is this line right here represents the potential energy for our oscillator. And it doesn't matter if it's the spring oscillator or the pendulum oscillator. It starts with potential energy. The potential energy becomes 0, and then it becomes potential energy again. The kinetic energy starts at 0, increases, and then becomes 0 at the maximum points. So the mechanical energy which is the sum of kinetic and potential energy, will stay the same through the entire process. And, since kinetic energy is 1/2 mv squared, it generally looks like a parabola when we plot it. So the potential energy will look like a parabola as well, just to kind of make up that difference there. And we can do all kinds of calculations, and we'll do some practice stuff in class as well, just to get comfortable with this. And really, the math is not that difficult. In fact, it's the same exact math we did in the previous unit. All right, longer video, but this concludes our unit on simple harmonic motion.